Okay, so I wanted to talk a little bit about PCA. So Aaron has given a great introduction to that. And what we really want, right, is that we don't want users to have all of these choices. We just want it to work fast, right? So we really want super fast, scalable computations of PCA on data stored on disk. We want to have like, easy use of multiple cores and nodes and so on. And we have made some progress there, but we're not there yet. Aaron has talked about BioC Singular, which is a substantial step forward in achieving this. But one of the things we are still working on is like making these algorithmic choices transparent. So I'm going to talk a little bit about that. So one complexity with this problem here is that we really want to access data stored on disk. And that means that performance is going to be a combination of computational workload of the algorithm and the data access pattern of the algorithm. So if you look at the various algorithms for computing fast SVDs, at the end of the day, the computational bottleneck reduces to either some matrix-matrix products or some matrix-vector products, which implies that if the data is sparse, we can use sparsity, and we can do these deferred tricks that Aaron talked about, where centering and scaling of the data doesn't destroy sparsity. There's a potential loss of precision when you do that, but in practice, that doesn't really seem to be the case. So what I'm focused on here is algorithms where we kind of compute the right eigenvectors of the problem. There's also a series of algorithms that are less well understood, where you kind of make some really approximations to those eigenvectors, and they're potentially even faster. So these algorithms make different trade-offs between computational speed and data access. So I've become a pretty big fan of the RLBA package, which is, in my experiments and benchmarking, without a doubt the fastest package for in-memory problems. It does way less computation than some of the other algorithms, but it touches the data more. Then there's RSVD, which is sort of a middle ground, and then there's sort of the old trick of reducing a very tall or very wide matrix to a cross product of itself, which is a theoretically embarrassingly parallel computation. But if the matrix is big, the cross product of the matrix in itself is a substantial computational overhead. So to put that into perspective, if you take a relatively small single-cell data set, the 8K data set, which easily fits in memory, RLBA is by far the fastest approach to doing a PCA on that data set. But data is accessed 34 times when you do a PCA on this particular data set. You get about a 240x improvement in computational speed, but you pay for it with data access speed. And that means that if we are running it through a sort of pipeline where data is stored on disk, you're really getting hammered on the data access pattern. So in practice, if you use our current stack for HDF5, it's 100 times slower to have data on HDF5 than to have it in memory, which is quite substantial in practice, right? So the question is whether or not this gap is something that can be, whether or not this gap simply implies that one should not use this algorithm that touches the data more, or whether or not this gap can be reduced by having faster data access. And it's a little bit unclear to me how fast we can actually potentially do on the data access way. And these are sort of some of the things that plays into these trade-offs, and also tells you that, sort of hints at the fact that the trade-offs you're making depends quite critically on the size of the problem. So we would really like to have like automatic selection of these things here. So it's all like, it all happens under the hood for the user, but that becomes pretty complicated. So one of the first things we want to do is, so one of the issues here is that we have a stack now that's built on delayed array.
Final minute, Kasper.
Yeah, which maps into HDF5, right? And they're sort of as we know, the file format can be optimized for different access patterns. We don't really have native sparsity in HDF5, which helps a lot with the computation, but is potentially a problem. And we have some overhead from the delay array framework. And altogether, this means that currently our stack with reading has a substantial penalty. And the question is like, how far can we get on that? So I've started making some more systematic benchmarking of these things here. Have a GitHub repository you can have a look at. Don't do it now because it's very much under construction. So we really need some systematic benchmarking of the really large problems to figure out where the trade-offs are. And I keep going. It's to the point where I keep going back and forth as to which algorithm I think is going to win in the end. It becomes very hard to reason about. But now with BioC Singular, we can definitely make some good steps forward here. Okay, that's me.
Thanks, Kasper. We'll switch to Davide.